This is benzene. This is hydroxybenzene or phenol. It has another name, that is carbolic acid. Carbolic acid, or simply this is called phenol. Another compound, this is known as benzaldehyde. So this is phenol and this is benzaldehyde. Another compound, this one, here both the groups present, hydroxyl group and aldehyde group. These groups are at ortho positions with respect to each other. Here, with respect to hydroxyl group, aldehyde group is at ortho position, and with respect to aldehyde group, hydroxyl group is at ortho position. Let us consider hydroxyl group is at ortho position with respect to aldehyde group. Then its name will be ortho hydroxy benzaldehyde, or this is position number 1, this is 2, then 2-hydroxy benzaldehyde. Simply this compound is known as salicylaldehyde. So this is commonly known as salicylaldehyde, ortho-hydroxybenzaldehyde or 2-hydroxybenzaldehyde, simply salicylaldehyde. In this lesson we are going to learn preparation of salicylaldehyde through Reimer-Tiemann reaction and mechanism of the reaction. So let us begin. Now let's see preparation of salicylaldehyde through Reimer-Tiemann reaction. To prepare salicylaldehyde, phenol is taken. Phenol is treated with chloroform in presence of base sodium hydroxide, and the reaction mixture is heated at 60 degrees Celsius temperature. Then phenol turns into this compound at ortho position aldehyde group, that is phenol turns into salicylaldehyde. Here byproducts are sodium chloride and water. If we balance this reaction, then here 3 chlorine atoms, 3 sodium atoms, 3 sodium atoms, and here there will be 2 molecules of water. Through this reaction we can prepare salicylaldehyde from phenol. This reaction is known as Reimer-Tiemann reaction. After German chemists Karl Reimer and Ferdinand Tiemann, German chemists Karl Reimer and Ferdinand Tiemann discovered this reaction, in which phenol is converted to salicylaldehyde. Reimer-Tiemann reaction is defined as the reaction at which salicylaldehyde is prepared from phenol in presence of chloroform and base sodium hydroxide or potassium hydroxide. In this reaction, inclusion of aldehyde group occurs at ortho position in phenol. Now let's see mechanism of the reaction. During mechanism of the reaction, we will see 3 molecules of sodium chloride are formed and 2 molecules of water will be formed. So now let's see mechanism of the reaction. Step 1, chloroform. CHCl3. In presence of base, chloroform produces proton from this hydrogen. This proton combines with hydroxide ion to form water. This minus sign indicates separation of water from reactants. So here 1 molecule of water is produced. Then what is left? This one. 2 electrons with negative charge. Then these 2 electrons from this bond, carbon-hydrogen bond. Carbon-hydrogen bond here undergoes heterolytic fission because electronegativity of hydrogen is 2.1 and carbon is 2.5. That is why this bond undergoes heterolytic fission. Now in the reaction mixture, sodium ion is present. This sodium ion takes out this chlorine atom as chloride ion. Now this chloride ion combines with this sodium ion to form sodium chloride. Here electronegativity of carbon is 2.5 and electronegativity of chlorine is 3.0. That is why this carbon chlorine bond undergoes heterolytic fission and chlorine gets removed as chloride ion. This chloride ion combines with sodium ion that is present in the solution to form sodium chloride. Now this is present, chlorine, carbon, chlorine. Here 2 electrons, these 2 electrons. The name of this entity is dichlorocarbene. Dichlorocarbene with 1 pair of electrons. So step 1 produces dichlorocarbene. Step 2, phenol. This is phenol. Phenol in presence of hydroxide ion, that is in presence of base, this bond shifts here to form carbon oxygen double bond and this hydrogen gets freed as proton. This proton combines with this hydroxide ion to form water molecule. So here 1 water molecule is removed and here another water molecule gets released. That is 2 water molecules get released from these 2 steps. Here we obtained this entity, double bond. Here carbon oxygen single bond turns into carbon oxygen double bond. Here double bond and here double bond. Now we can show in 2 steps. Here electron repulsion is created. To reduce this electron repulsion, these pi bonded electrons move here. Then this is formed. Hydrogen is present here and this is minus charge because pi bonded electrons turn into lone pair of electrons. That is, step 2 produces this species. Now let's see step 3. Minus charge, dichlorocarbon with one pair of electrons. Here orthocarbon carries one pair of electrons, that is orthocarbon is negatively charged here. Now this orthocarbon forms coordinate covalent bond with this carbon of dichlorocarbon. Then this is formed double bond, here oxygen, hydrogen, carbon, chlorine. In this case we see that dichlorocarbon, here carbon receives one pair of electrons from this entity, and as a result this coordinate covalent bond is formed, in which carbon receives one pair of electrons from this carbon. As a result, over carbon negative charge is developed because carbon received one pair of electrons from this carbon. That is why this negative charge. Then this happens, that is pi bonded electrons move towards oxygen because oxygen's electronegativity is 3.5 and carbon 2.5. Then electron deficiency is created over this carbon. As a result, this electron turns into carbon-carbon bond. Carbon-hydrogen bond turns into carbon-carbon double bond. And here, this hydrogen gets freed as proton. This proton combines with hydroxide ion. Not hydroxide ion. This proton combines with this carbon. Then this is obtained. Oxygen with negative charge. Then here again carbon-carbon double bond. Then carbon, hydrogen, here chlorine, here another chlorine. That is now carbon, then this hydrogen, carbon-hydrogen new bond, carbon-chlorine, 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 carbon-chlorine. This is formed at step 3. Step 4, this one participates in step 4. Oxygen with negative charge, carbon, hydrogen, chlorine. Solution contains sodium ion. Because of the presence of sodium ion, this chlorine gets freed as chloride ion. This chloride ion combines with this sodium ion to form sodium chloride again. Now this is obtained. Oxygen minus, here carbon, hydrogen, chlorine, carbon chlorine, and positive charge, because this chlorine gets freed as chloride ion through heterolytic fission of carbon chlorine bond. That is why this carbon gets positively charged. Now solution contains hydroxide ion that combines with this carbon. Hydroxide ion combines with this carbon to form this species. Oxygen negatively charged, carbon hydrogen, carbon chlorine, here oxygen hydrogen, that is carbon oxygen hydrogen, carbon oxygen hydrogen. Now we get salicylaldehyde, reacting with sodium ion, that is sodium ion receives this chlorine as chloride ion. This chloride ion combines with this sodium ion to form sodium chloride molecule. Now this hydrogen oxygen bond, oxygen hydrogen bonding electrons turn to carbon oxygen double bond. This hydrogen gets freed as proton. This proton combines with this oxygen to form oxygen and hydrogen, that is hydroxyl group. Here this oxygen turns into hydroxyl group and this group turns into CHO group, CHO. This hydrogen gets freed as proton, this chlorine gets freed as chloride ion, and ultimately this compound is obtained, that is salicylaldehyde. This is the way by which salicylaldehyde is obtained through this reaction, Reimer-Tiemann reaction. Reaction discovered by German chemists Karl Reimer and Ferdinand Tiemann. Salicylaldehyde is an important organic compound from which many compounds are prepared. This is all about Reimer-Tiemann reaction. No more today. Thank you very much.